Hey everyone, and a massive, warm welcome back to the channel. It's truly awesome to have you here today. Before we dive deep into one of the coolest, literally, concepts in physics, I want to take just a moment to send out the very best wishes to you all. Wherever you are watching this, whatever you're doing, I genuinely hope you're feeling strong, healthy, and full of positive energy. May you and your loved ones be blessed with excellent health and happiness always. Okay, let's bundle up mentally and explore the ultimate limit of cold, absolute zero. Right now, you're experiencing a certain temperature. Maybe it's warm where you are, maybe it's chilly. We measure temperature using scales like degrees Celsius or degrees Fahrenheit. We know that 0 degrees Celsius is when water freezes and 100 degrees Celsius is when water boils. But have you ever wondered, is there a point where things just can't get any colder? Is there a rock bottom for temperature? The answer is a resounding yes, and it's called absolute zero. Absolute zero is the absolute coldest temperature that is theoretically possible anywhere in the entire universe. On the Celsius scale, this mind-blowing temperature is exactly negative 273.15 degrees Celsius. Think about that number for a second. Negative 273.15. That's incredibly, unimaginably cold. To understand why absolute zero exists and what it means, we need to think about what temperature really is. Forget about numbers on a thermometer for a moment. At its most fundamental level, temperature is all about movement. Specifically, it's about the jiggling, vibrating, dancing motion of the tiny particles, atoms and molecules that make up everything around you, including the air you breathe and even your own body. When something feels hot, it's because its atoms and molecules are moving around very, very fast, bumping into each other with a lot of energy. Think of a pot of boiling water. Those water molecules are zipping around furiously. When something feels cold, its atoms and molecules are moving much slower. In a block of ice, the water molecules are still vibrating, but they're locked in place, jiggling in a much more restricted way. The colder something gets, the slower its particles move. Now, imagine you could somehow take an object and start pulling energy out of it. Every time you remove energy, you slow down the frantic dance of its atoms and molecules just a little bit more. You make it colder and colder. Absolute zero is the theoretical point where you've removed all the kinetic energy, all the energy of motion you possibly can from those particles. At absolute zero, the particles would stop jiggling, vibrating, and moving entirely. They would reach a state of complete and utter stillness. This is why it's called the absolute zero. It's the point where the thermal motion of particles hits zero. There's simply no lower energy state possible for them to be in. It's the ultimate stop sign for cold. You might think, okay, so let's just build a super freezer and cool something down to negative 273.15 degrees Celsius. But here's the crucial, fascinating, and maybe slightly frustrating part. Reaching absolute zero is impossible. It's a limit we can get incredibly, mind-bogglingly close to, but we can never quite touch it. Why? Because of the fundamental laws of nature, particularly the laws of thermodynamics. Think of it like trying to perfectly balance a pencil on its sharpened tip. You can get it really close to standing perfectly upright, but the tiniest breath of air, the slightest vibration, will always knock it over. Similarly, in the quantum world that governs atoms and molecules, there's always some tiny, irreducible amount of energy present. You can cool a system down to within a billionth of a degree above absolute zero, but removing that last, minuscule bit of energy becomes infinitely difficult. It's like trying to perfectly smooth out the very last wrinkle in a sheet. The closer you get, the harder it is to make any further progress. The universe itself seems to prevent us from achieving perfect, motionless stillness at the atomic level. Getting close to absolute zero, however, is not only possible but has led to some of the most astonishing discoveries in physics. Scientists use incredibly sophisticated techniques involving lasers and magnetic fields to slow atoms down and trap them, chilling them to temperatures just a fraction of a degree above absolute zero. At these ultra-low temperatures, the weird and wonderful rules of quantum mechanics, which are usually hidden at everyday temperatures, come dramatically to the forefront. One of the most famous effects is superconductivity. Normally, when electricity flows through a wire, it meets resistance. Think of resistance like friction for electricity. It makes the wire heat up and wastes energy. But when certain materials are cooled to extremely low temperatures, close to absolute zero, something magical happens. All electrical resistance vanishes. Electricity can flow through them perfectly, forever, without losing any energy. This isn't just a lab trick. It's used in powerful magnets for MRI machines in hospitals and holds promise for revolutionary technologies like lossless power grids and incredibly fast computers. Another bizarre phenomenon near absolute zero is superfluidity. Imagine a liquid that can flow without any friction whatsoever. If you stir a cup of superfluid liquid helium, cooled close to absolute zero, it will keep swirling around forever, never slowing down. It can climb up the walls of its container and drip out over the edge, seemingly defying gravity. It can squeeze through impossibly tiny pores that would stop any normal liquid. This happens because at such low temperatures, all the atoms in the liquid fall into the same quantum state and start acting like a single, coordinated superatom, moving in perfect unison without any internal friction. It's like a crowd of people suddenly moving as one perfectly synchronized dancer, gliding effortlessly. Even the atoms themselves behave strangely near absolute zero. At room temperature, atoms zip around like hyperactive bees. But cool them down significantly, and they slow way down. Get them incredibly close to absolute zero, and their movement becomes so sluggish that their wave-like nature, as predicted by quantum mechanics, becomes impossible to ignore. Scientists can use laser beams to create optical molasses, effectively trapping atoms and cooling them until they are moving so slowly that their quantum waves overlap. When this happens, all the atoms lose their individual identities and merge into a single, giant matter wave. This unique state is called a Bose-Einstein condensate. It's like taking thousands of distinct ripples on a pond and merging them into one single, massive, coherent wave. Studying Bose-Einstein condensates helps us probe the deepest mysteries of quantum mechanics. It's also fascinating to think about absolute zero in the context of the universe itself. Outer space is cold, incredibly cold. The vast emptiness between stars and galaxies has a background temperature, measured from the faint afterglow of the Big Bang called the cosmic microwave background radiation. This temperature is about -270 degrees Celsius. That's only about 2.7 degrees Celsius above absolute zero. So, even the depths of space, the coldest natural environment we know, is still a couple of degrees warmer than the ultimate cold limit. There is nowhere in the vast cosmos that naturally reaches absolute zero. It's always just a little bit warmer. Understanding absolute zero also helps us grasp the meaning of temperature scales. The Kelvin scale, used widely in science, is directly tied to absolute zero. 0 Kelvin, written as 0K, is absolute zero. -273.15 degrees Celsius equals 0 Kelvin. The size of 1 degree on the Kelvin scale is the same as 1 degree on the Celsius scale, but Kelvin starts at the true bottom, absolute zero. So, room temperature, around 25 degrees Celsius, is about 298 Kelvin. Water freezes at 273 Kelvin and boils at 373 Kelvin. Using Kelvin makes scientific calculations involving temperature, especially in physics and chemistry, much more straightforward because you never have to deal with negative numbers representing physical temperatures. 0K is the absolute minimum. The quest to reach closer and closer to absolute zero pushes the boundaries of our technology and our understanding of the universe. It reveals a hidden quantum world where particles behave like waves, liquids flow without friction, electricity travels without loss, and matter coalesces into strange new states. It shows us that even the concept of cold has a fundamental limit imposed by the very nature of energy and motion. Absolute zero is a stark reminder of the profound connection between heat, motion, and the restless energy that permeates all matter. While we may never quite reach that ultimate stillness of -273.15 degrees Celsius, The journey towards it continues to unlock secrets about how our universe works at its most fundamental level. So next time you feel a chill, remember the incredible journey downward to the ultimate cold, a place of quantum wonder that remains just out of reach, defining the very limits of temperature itself. Thanks for exploring this icy frontier of physics with me today. Stay curious.